in continuation of our discussion of probability distribution, today we will be discussing continuous probability distribution. Last few classes we have discussed discrete probability distribution, as well as we have done some tutorials also on the discrete probability distribution. Now we will be discussing continuous probability distribution. This continuous probability distribution, I will be taking 2 lectures for it. In the first lecture we will be covering around 3 continuous probability distribution, and other 3 I will be covering in the next lecture, followed by a tutorial class. So, in this lecture I will be covering uniform distribution, normal distribution and standard normal distribution. Now, before going to uniform distribution, let us first take a quick recap of what we have learned of discrete probability distribution. The left side figure shows the discrete probability distribution. In discrete probability distribution, remember how like we can express a discrete probability distribution in the form of a tabular form, in the form of a graph, as well as in the form of an expression. The figure here shows that we have expressed the discrete probability distribution in the form of a figure. So, now can you remember what figure is this? It is a bar chart, right? So, how I can distinguish that it is a bar chart, not an histogram? Because in a histogram there will not be any gap between the this rectangles. Okay, let me take the pen and then I will be showing you. So, can you see this gap? Yeah, this gap in a histogram, this gap will not be there. Basically, there will not be these gaps, it will be just close together, because the width of this rectangle, this width of this rectangle in a histogram, it refers to the range of the values. So, we cannot put any gap in between 2 rectangles. So, this figure directly shows that it is a bar chart. Anyway, that is not the main concern. Main concern is here I am just trying to say you how we basically can have a figure of a discrete probability distribution. Similarly, for continuous probability distribution, the figure is in a continuous curve. So, here we see this is a continuous curve. So, in this continuous probability distribution, the figure is basically a continuous curve. So, now the thing is that first again I will just will just go back a bit and we will see what was f x. In case of a discrete probability distribution, what was f x? F x is the probability of the random variable x, the probability that the x takes, that the random variable x takes, that is f x. So, value of f x cannot be greater than 1, it cannot be less than 0. So, f x has to be between 0 and 1. That is the case in case of discrete probability distribution. But in case of continuous probability distribution, I have already mentioned, if you can remember, of course, f x cannot be less than 0, it has to be greater or equal to 0, but f x can be greater than 1 also, because here f x does not denote the probability. It is here f x is a density function, how much the probability concentration is there within a certain interval. When you want to find out the probability for continuous, we will have to find out the area within that interval. Suppose I am considering this area, suppose this area. So, this area I will have to find out the area of this area, I will have to find out the area of this region. Suppose this is A, this is B, I will have to find out the area of this region to find out the probability at this point. Sorry, it cannot be when speaking of continuous probability distribution, it will never be at a single point. I already have mentioned that probability at a single point is equals to 0, it is almost equals to 0. So, when we talk of probability in continuous domain, it has to be within an interval, maybe a very small interval, maybe a bigger interval. And of course, for a random variable, for a function to satisfy a continuous probability distribution, rather I should say function to satisfy a probability density function. So, we can say it is a probability density function when it satisfies 2 of the properties. If you remember, I am just putting it here again. It is called a probability density function. The first condition is that f x should be greater or equal to 0, and integration of f x from all the range from minus infinity to plus infinity, it should be equal to 1. These are the 2 conditions. So, and now if I want to find out the probability in 2 values, that a and b, in the figure it is given this a and b. So, how we can find out? It is just the integration of f x within the value a to b. That is how we do in continuous random variable, when the variable is continuous. So, for finding out the mu and that is the mean and the variance, mean, or I should say the expected value on the variance, it is same as what we have done for discrete probability distribution, but instead of summation here, there we have used summation, here we will be used integration, mu f x, integration of x f x, and for sigma it is integration of x minus mu whole square f x. It is the same, just summation get replaced by integration, because here we are concerned of the formula, the area within that range. So, we will be basically integrating it. So, one of the simplest continuous probability distribution is the uniform distribution. So, we talk of uniform distribution where the probability at each point is same. So, basically if I can tell you about the graph of a probability continuous uniform distribution, it will be this sort of a graph here. So, we are trying to find out within the range the A to B. So, this is the graph here. So, it is equal probable in all the areas, and of course, since it is a probability distribution, so some integration of f x should be equals to 1. So, if integration of f x is equals to 1, so what it will be, what will be the probability of this, probability of any value in probability in this range, what is the probability? It will be 1 by b minus a, isn't it? So, probability will be, so f x will be, my f x will be as what it is given here, f x will be 1 by b minus a. Directly we can get it, since the area, if we find out the area of this whole rectangle, area of the whole, this area of the rectangle is what, length into breadth. If now this is my, I have to find out my probability in this area, this whole area has to be 1. So, what it will be, to when will I get 1? Because my length is, total length is b minus a, that means I have to get it 1, I have to multiply it 1 by b minus a. That directly gives me the probability, isn't it? That I should not say probability, that directly give me the density function, that is f x. Okay, it is not probability, mind it is the f x. So, my f x is 1 by b minus a. 1 by b minus a from the range x ranging from a to b, and in other areas it is 0. Okay. So, now if we are interested in finding out any value within this range, suppose we are interested in finding out what is the probability in this range C to D. So, what will be the probability in this range within in C to D? My what is my length of this area? Length of this area is this d minus c. Okay. So, d minus c into what is my density function? Density function is 1 by b minus a. So, my probability becomes d minus c by b minus a. So, that is the probability within the range C to D. Probability always in continuous probability distribution, I am repeating it again. When we talk of continuous probability distribution, the probability is always within a interval. We do not talk of a single point. So, here by using the formula, same formula, integration of x f x for expected value, we will be getting a plus b by 2. For sigma square, we will be getting b minus a by 2, where b and a are the range of the random variable, where x is the random variable, can take value within the range of a to b. Now, one example to illustrate our continuous uniform distribution. Remember, uniform distribution we had it for discrete also. Similar, we have uniform distribution both for discrete and continuous. Now, coming to this example, say this example, if you go to the example, you will find it is very easy. Like what it is given, suppose that a large conference room at a certain company can be reserved for no more than 4 hours. The large conference book, we cannot book it for more than 4 hours. That means, my value of my random variable, it ranges from maximum 0 to 4. Booking cannot be negative, right? Though when we talk of continuous probability distribution, so it can be minus infinity to plus infinity, but here booking cannot be negative. So, it will be from 0 to 4. The rest all other places, the random variable, the probability of the density function will take the value 0. So, then both long and short conference can occur quite often. In fact, it can be assumed that the length x of a conference has a uniform distribution on the interval 0 to 4. It is specified that the length x, here x is the random variable, x is a uniform distribution in the range of 0 to 4. If the x has a uniform distribution in the range 0 to 4, then what is the probability density function? That means, what is my f x? My f x is equals to 1 by 4, isn't it? Just 1 by 4 minus 0. I have to find it from this range. This is 0, this is 4. Okay? This is my range. So, my probability density function will be 1 by 4 minus 0, that is 1 by 4. So, that is my f(x). So, first question, what is the probability density function? That is all. It is 1 by 4 from which range? From 0 to 4, and rest all other area, what is the range? It is 0. What is the probability density function other than this range? That is from 0 to 4, it is 0. That is how we define the density function. See here the density function, it is 1 by 4 from 0 range to 0 from x ranging from 0 to 4 and 0 is elsewhere. Now, what is the next question? What is the probability that any given conference lasts at least 3 hours? So, it is given that any given conference lasts at least 3 hours. So, that means my random variable will go from 3 and above. Okay. So, I will integrate it from 3 to 4. So, that is a p of x delta equals to 3, that is simple integration from 3 to 4, 1 by 4 dx, that is all, that is it. That is a very easy problem. Now, we will discuss the next important distribution, that is normal distribution. It is also Gaussian distribution. This is a very important distribution in the sense that this distribution has wide application. You can see this application of this in nature, you can see application of this in industry, research, business, many places you can see this application of this normal distribution. This distribution was discovered by Professor Carl Gauss. That is why by his name it is, this distribution is also called Gaussian distribution, and this distribution, it has a basically bell shape. Okay. So, this is called a bell shaped curve. It described any phenomenon that occur in nature, industry and research. Some of the example is meteorological example, rainfall studies, measurement of manufacturing parts, etc. Well, let me tell you what made this Professor Gauss to discover this distribution. Actually, he was trying to measure the movement of celestial body. He was trying to measure the movement of celestial body again and again of one celestial body. He was trying to measurement its movement. On each measurement, he was getting different value. So, when he was trying to see there is an error in this error in each measurement, he saw that it fits into a distribution. That distribution, that he has come up with this distribution based on this error and measurement, that is this bell shaped distribution, that is the Gaussian distribution. So, when I was discussing discrete probability distribution, I have already specified that when we talk about distribution, there are a few parameters which specify a distribution. Likewise, uniform distribution also we saw that parameters that describe the uniform distributions are mu and variance, mu and sigma. So, sigma, if I tell sigma is a standard deviation. Like similarly, for normal distributions, the parameters that are mu and sigma here also, where mu is the mean and sigma is the standard deviation. Well, let me tell it in a different way. Actually, when we talk of a distribution are characterized by few parameters which are called maybe scale parameter, shape parameter, location parameter. Okay. So, instead of telling us mu or standard deviation, that a parameter is defined by scale. What is the scale of the distribution? So, then parameter is defined by the location where it is centered, basically the expected value, the mu, where it is centered, that is the location. Then we have something called a shape parameter. What is the shape of the distribution? Shape of the distribution, like as I talked in discrete probability distribution, I told you we are not very much concerned about the state of the distribution while talking about discrete probability distribution. Actually, we do not bother that much about the shape, but in case of continuous probability distribution, when we are talking about the distribution of a continuous random variable, shape plays an important role. So, there is a shape parameter as well. Now, these parameters, these are also called moment. I have not kept it in the slide because this is you do not need to consider as a part of this course, but for your knowledge, for your information, I am just telling this we can also call the moments. There are different moments which characterize a distribution. The first moment is the expected value, that is the mean, that is the location. Then the second moment is the scale parameter, that is the standard deviation, that is the spread, how spread out my distribution is. what does variance gives? How spread out it is, right? So that is the second moment. Then third moment is symmetric. How symmetrical is my distribution? Whether it is skewed towards left, it is skewed towards right, or it is centered, it is symmetrical to the mean. So that is the third third moment. Then fourth moment is the kurtosis. Kurtosis give the piquetness of the distribution, and that is the height of the distribution. Okay, so these are there are many other moments also. These four moments are very necessary to characterize a distribution, but we will not go and discuss the moments here, but we will just stick to the parameters which are necessary to describe a distribution. So, talking of normal distribution, the parameters that describe a normal distribution basically it's the mean and the sigma. Mean is the location parameter and sigma is the scale parameter. Here we do not have the shape parameter. Why? We do not have the shape parameter because when we talk of normal distribution just has one shape, that is the bell shape, just this one shape. So, we do not have a special parameter to differentiate the different shapes that may take. Since normal distribution has just one shape, no point. So, normal distribution has just two parameters, that is mu and sigma. It is also called the location parameter as well as the scale parameter. Now, this is the probability density function for the normal random variable. If x is a normal random variable, so this is the density function. Like for uniform distribution, what is the density function? Density function is the f of x is equals to 1 by b minus a, where x ranges from b to a. Here say x ranging from minus infinity to plus infinity, my f of x is this particular expression. Fine. Now, okay, I will come to this expression again, but before that let us see some shapes of the normal distribution. Like here you can see different bell curve. First one you see where if my sigma 1 is equals to sigma 2, both the here we have see two bell curves where sigma is same for both the case, but that means that my spread is same, but the location is different. One location is mu 1, the another location is mu 2. You see how it is both. Then you see this this one. Here the location is same, that is mu 1 is equals to mu 2, but both the scale is different. Okay, for where here what is it? Sigma 1 is smaller. Sigma 1 is smaller than sigma 2. Sigma 2 is more, that is it is more spread out. Okay. Similarly, here we see the third one where mu 1 is less than mu 2 and sigma 1 is less than sigma 2. This type of figure we basically get for different values of mu and sigma. So, now for a normal distribution, what the properties are, the curve is symmetric about the vertical axis through the mean mu. Okay. The curve is symmetric to the mean mu, whatever may be the mean. If this is my mean, suppose this is my y axis, suppose this is my mean, my curve is symmetric towards the mean. Okay. And we also know what is mode. See, the mode is the point which is the point on the horizontal axis where the curve is maximum. In a normal distribution, curve is maximum at the mean, at the expected value at mu. So, mode is also mu here, and for normal distribution my median is also mu here. What is median? 50% of the at median 50% of the population falls in the left of the median, other 50% falls to the right of the median. So, here in normal distribution mu is also the median also. In a normal distribution, mean is equals to mode is equals to mean. This is a very important characteristic, please remember. The total area under the curve, of course, it has to be 1 in any for a continuous probability distribution. We have seen f x gives the shape of the curve and the total area under the curve is equals to 1. That is why we integrate f x from integration from minus infinity to plus infinity, we get 1. Okay. So, this is the integration, we get this whole is equals to 1. So, now what is mu? Mu is integration x f x and sigma square is integration x minus mu whole square then f x. Just put it in the value and then we have to simplify it. So, if we are interested in finding out what is the probability in this range x1 to x2, it is given here. If you want to find out what is the probability within this interval x1 to x2, just we have to integrate the fx value, whatever fx expression we have to integrate fx from x1 to x2. Okay. Now, see the problem here. When we are interested in finding the probability of this range x1 into x2, maybe any other range, whatever range may be, if we are interested in finding out the probability, then see we will have to evaluate this expression. Evaluate this expression for the particular range. Evaluating this expression is not a very easy task. We will have to do this. There is a complex integration. Solving this complex integration again and again for when trying to find out the probability of any interval, it is a tedious job. So, this job is made easy. It can be, I should say, it can be made easy if we have a standard lookup table, like what we see in the binomial distribution. I told you that we have a table. I also showed you, remember. Similarly, if we can have a lookup table, then instead of doing this computing this integration again and again, we can refer to the table and we can come to the value. That will be very easy. So, now the problem is that how many tables we will have, because this value, this expression will have different values for different mu and different sigma square. My mean and sigma can be anything, it can be any value, right. Mean can be starting from 1, 2, 3, 4, y1, it can be 0 also, it can be any value. Even sigma also, it can be any value. So, we will have to have different tables for different values, isn't it. So, that is not possible. So, it is really not possible to have a normal table for such a case, but there is a rescue. But we can, the rescue is that we can transform this normal random variable, we can transform this normal random variable to a Z distribution. It is called Z distribution, and the corresponding distribution is called standard normal distribution. How, when we can transform this x to Z distribution, what happens? Then our mean is always 0 and the variance is 1. So, that means if we have a table for mean 0 and variance 1 for different probabilities values, then it is very much feasible, we can have that, we can look up the table. So, there are standard lookup table where we can find the value of the normal distribution, but this random variable, normal random variable, first we have to convert it to Z value. So, once we can convert it to Z value, its corresponding distribution of this Z value has a mean of 0 and variance of 1. So, this is just how we can convert this Z to x, normal random variable x to Z. This is the formula, Z is equals to x minus mu by sigma. So, we need to convert x, our random variable is x, isn't it? We need to convert x to Z. How we will convert? So, Z is equals to x minus mu by sigma. So, what we got is a Z distribution, or it is also called standard normal distribution. It has a mean of 0, always its mean will be 0, this is the y axis, it will be always mean will be 0 and standard deviation is 1. So, we need just a couple of lookup tables with mean 0 and standard deviation 1, but having different, because probability might be different, isn't it. So, for the different probability of occurrence, we can have different tables, that is all. So, we will see some examples. So, that is what, see here how the expression, this was the expression, remember this was the expression for fx, if we are interested in finding out the values between in the interval x1 to x2. So, this was our expression. Now, what we have taken? We have taken Z is equals to x minus mu by sigma, isn't it. Now, what will be dz? Dz is equals to what? 1 by sigma dx, 1 by sigma dx, this is dx, 1 by sigma dx, right, that is dz. So, here in this, if I can substitute x minus mu by sigma square, x minus mu whole square by sigma square, this sigma square is here. If I can substitute by z and then substituting dx by sigma this dz, so I will be getting this, okay, and this value I can get it from the table. But again, one more thing, there is one more point to that. The table, it has, the table has the cumulative value. the table what we will see, like in binomial distribution table had the cumulative value, right, cumulative probability distribution function value. Similarly, here also normal table it has the cumulative distribution value. So, cumulative means I will have the value say from minus infinity to a particular value, say to a particular value, say z, whatever is z, okay, and this expression e to the power minus 1 by 2 z square dz. This value will get it from the table. So, once we can get it value, we can, if we can get this value from the table, our job is done. Fine. That is what the figure shows, the difference between the standard normal distribution and normal distribution, what I have already discussed. Now, see how we can look up the table. So, here table, this is the table. Suppose in the figure, see in this figure, there was some x I have found out from what is this, z is equals to x minus mu by sigma. By substituting mu and sigma value, suppose I got my value of z as 1.05. Now, I will have to find out the probability corresponding to that, means probability corresponding to 1.5 means integration of this value from minus infinity to a particular value, right. So, whatever to this value of z, that is 1.05. As I told you, it always gives the cumulative value. So, how do I look the table? See, here is the, so in the vertical you will see this is z value, vertical and horizontal both are z value. How we find? In the vertical you see this yellow color, this is 1. I need 1.05. So, this is 1, this is 0.05. So, that is total together is 1.05, and where it meets, this is my probability. This is my probability 0.8531. So, if as I told you standard normal distribution median is 0. So, this is 0, if this is the curve, this is 0. So, 1.05 z value of 1.05, it will be towards the right of 0, right. So, this is my z value 1.05, and what is this area? This area is basically the probability that my value will lie in this range. Area is nothing but the probability, right. So, this area is 0.8531. Okay, this is how we look into the table. We will in the tutorial class we will be doing here also, of course, we will be doing some problem, but tutorial class will be doing more problems and things will be more clear. Then say given a standard normal distribution, find the area under curve that lies to the right of z is equals to 1.84. To the right of z is equals to 1.84. So, right of z is equals to 1.84 means if this is my curve, z is equals to 1.84, because this is 0, my z value will be somewhere here 1.84, right, means I need to find out this area. So, what my graph will give, my table will give this area left of this. Table is the cumulative, it will start from cumulative means from minus infinity to 1.84, I will get this value, but I need this value, that means 1 minus of that I will be getting this value, right. So, here you see, so it is 1.84, this is 1.8 and 0.04 will make it 1.84. So, I got this is the value, then 1 minus of that is whatever value I needed, right. Similarly, between the z is equals to 1.97 minus 1.97 and z is equals to 0.86. So, it is asking between z is equal to 1.97 and 0.86. How we will do here? Suppose, let me take the table, then it will be better. So, it is asking some minus 1 point, I do not remember what was it, say minus 1.5, suppose whatever it was in the question, I do not remember, and it was asking from minus 1, sorry, it is not 1.5 will not be this, I need an eraser here. So, minus 1 point, there will be something here, say minus 1.8, whatever it is, because this is 0, minus will be this side, and between 0.86. So, my 0.86 may be say this value 0.86. So, I need this area. Okay, I need to find out this area. That means basically I need to find out this area means what it is asking. I need to find out what is the probability that my random variable will lie in this range 1.86 to 0.86. Okay. So, when I am interested in finding this area, my cumulative table will have all the values to the left of it. So, if I see 0.86, I will be getting this value from minus infinity to this value. Okay. And then when I am looking for 1.8, from here this portion. Okay. But my intention is finding out this portion with between this. So, how will I find between this? Whatever value I got from 0.86, from this value if I subtract this value, I will get this value, right. So, that is how we look it from the table. Okay. Fine. Similarly, given a standard normal distribution, find a value of k such that b probability of z greater than k is 0.315. Okay. Now, we have to find out what is k here. So, it is given greater than k. In the cumulative table, it is always less from minus infinity to a particular value. So, first when it is z greater than k, what we have done, first we have tried to find out what is less than k. So, z less than k is this value 0.6949. Now, from the what is the value of k corresponding to this area, this is the all this here in the table, all the entries are nothing but the area within this curve. So, here it is 0.6949. So, I found 0.6949 is this value. So, what is corresponding to 0.6949? Here it is 0.5, here it is 0.01, that means 0.51. My k value is 0.51. Fine. So, one problem, given that x has a normal distribution with mean mu is equals to 300 and sigma is equal to 50, find a probability that x assumes a value greater than 262. Okay. Oh no, sorry, this is a there is a slight mistake. Okay, this is the question. Given that x is a normal distribution with mu is equals to 50 and sigma is equals to 10, find a probability that x assumes a value between 45 and 62. So, first between 45 and the value of the random variable is 45, value of the random variable is 62. This x I will have to first convert it to z. So, what is corresponding to x 45, what is the z value? I found z value is minus 0.5. Corresponding to x value 62, my z value is 1.2. Okay. So, if we can see the figure, that means I am interested in this area, in this blue shaded area. I want to find out what is the probability that my random variable will take the value from minus 0.5 to 1.2. But in the question it was between 45 and 62. 45 and 62 get transformed to minus 0.5 to 1.2. So, from the table I can get this value. What is the probability of getting 1.2? Minus infinity 1.2. Then again I can get what is the probability of getting the value minus 0.5, I will get this value. So, from this whole value, if I minus this value, I will get the blue portion, that is the area of this blue portion, that is the probability. Okay. So, that is how we solve this sort of problem. So, we will be doing some real application of normal distribution in our tutorial classes. So, now in this lecture basically we learned continuous uniform distribution, we learned what is normal distribution, what is standard normal distribution, and we have solved some problems, though more problems will be solving in our tutorial classes, and in the next lecture we will discuss some more continuous probability distribution. With that, okay, these are the references, okay, and thank you guys.